In this one, we're going to be taking a look at how to find the matrix of a transformation given a linear transformation. So we are looking for the matrix A such that the image of a vector that we refer to as x is going to be the same as multiplying matrix A times x. So given T, find A. Now in this example that we're looking at right here, we have T of a vector x1, x2, x3, and we see that the image of this vector has four components: x1 minus 2x2 plus x3, 2x1 minus x3, 5 times x2, and negative 3 times x1 plus 4 times x3. My goodness, that is a lot going on. Well, the first thing that I want to point out here is what the domain and the codomain are. Now with that in mind, we're taking T of a vector that is in R3, and we are sending it to a vector that is in 1 component, 2 components, 3 components, 4 components, R4. So that means that our vector x will be expressed in terms of a 3 by 1 matrix, and T of x will be expressed in terms of a 4 by 1 matrix. So at the very least, we should figure out what the relative size of the matrix A is. Now there are going to be two different methods that we're going to talk about how to do this. So first thing I want to do is set up on the right hand side AX, and then on the left hand side we'll set up T of x. So x we have established is going to be a 3 by 1. Let's see, 3, I write 3. So x1, x2, x3. X is officially a 3 by 1. And what it's supposed to be equal to is this vector right over here. So x1 minus 2x2 plus x3. 2x1 minus x3, 5x2. Excuse me, my goodness. A little dusty today. And it is supposed to be equal to this image vector. Now, this would be considered a 4 by 1. Now, the idea is that for our matrix A, it's going to have some size right here. These two numbers are going to have to be the same. And the size of the result is going to be this size right here. So this lets me know right away that the number of columns of A is going to be 3, and this over here lets me know that the result is going to have 4 rows. So we are looking for a 4 by 3 matrix. So make it a little bit taller than our 3 by 1. So the idea is if I multiply the first components and the second components and the third components all together across each row, I should be getting the result that's in the corresponding row of the image vector. So I'm seeing this as 1x1 minus 2x2 plus 1x3. So my three components would have to be 1x1, negative 2x2, and 1 for x3. The alternative would be to simply read this from left to right and copy down the coefficients in the order that you see them. By the same logic, for the second row, the second component, I'm seeing 2x1, no x2, and negative 1x3. So 2, 0, negative 1 is what we can expect to see for the second row. In the third row, I'm seeing simply a 5 for x2, meaning that x1 and x3 are not present. And finally, for x3, or excuse me, for the fourth row, we read this from left to right. We get negative 3x1. There is no x2, so 0 for x2, and 4 x3. So in that regard, we're very much reading these things from left to right when we read the image vector. There is, however, another way to make this happen, and I'd like to demonstrate. The other way to make this happen is to actually calculate T of our standard basis vectors in R3. This explanation makes a lot more sense after you've actually seen this part up here. So T of 0, 1, 1 is saying let's plug in x1 equals 1, x2 equals 0, and x3 equals 0. The first component will be 1, second component will be 2, third component will be 0, and the fourth component will be negative 3. How does that relate to the matrix that we just created? Well, 1, 2, 0, negative 3 is actually the first column of A. If we do the same thing by setting x1 and x3 equal to 0 and setting x2 equal to 1. For the first component, we'll get negative 2. The second component will get 0, since there is no x2 term there. For the third component, we'll get 5. And for the fourth component, we'll get 0. Negative 2, 0, 5, 0 is the second column of the matrix. And for 0, 0, 1, that's plugging in 0 for x1 and x2, and then plugging in 1 for x3. In the first entry, we'll get a 1. In the second entry, negative 1. In the third entry, there is no x3 there, so that'll be 0. And in the fourth entry, we'll get 4. 1, negative 1, 0, 4 happens to be the third column of A. So these are two different techniques that you can use to obtain either the rows of A by interpreting the coefficients of the image, or by taking the image of the standard basis vectors, you can get the columns of A. You don't have to like both of them, but you do have to get used to using one of them to find the matrix of A.